everyone, today I'm going to be talking about saponification, also known as base-promoted ester hydrolysis. Seen here is the general formula, where an ester is cleaved into a carboxylate and an alcohol through the addition of water and an inorganic base, very commonly NaOH. The word saponification comes from the Latin root sapo, meaning soap, and this process is very commonly used in soap making. In this general formula, the first step is a nucleophilic attack by a hydroxide group. The second step is the removal of the leaving group, or the R' side chain. The third and final step is deprotonation, when the hydrogen is removed and donated to the oxygen, which is also attached to the side chain. To look at a more specific example of saponification, we can use triglycerol. Triglycerols are hydrolyzable lipids, meaning they are broken down into smaller pieces through hydrolysis reactions. The first step is that the hydroxide group acts as a base and reacts with the carbon in a nucleophilic addition reaction. The electron lone pairs on the hydroxide group are attacking the carbonyl group here, which causes the electrons to move up and join the oxygen. Therefore, the oxygen becomes an anion or carbanion. When the double bond becomes more stable and reforms here, the OR- group leaves as a strong base. The strong acid transfers a hydrogen proton to the OR- group, moving the lone pairs back onto the electronegative oxygen. A carboxylate anion is left, and the base-promoted ester hydrolysis is complete because the ester linkage has been broken. Saponification values, or numbers, indicate the amount of base needed to saponify a fat sample. Most commonly, they're listed in KOH, or potassium hydroxide. So the saponification value is the milligrams of KOH needed to saponify 1 gram of fat under the specific conditions. An example shown here is avocado oil, which requires 0.186 milligrams of KOH to saponify per gram. For a comparison model, we can look at magnetizing a needle. The needle in this case would be the ester in the saponification reaction, and rubbing the needle on a magnet at least 50 times is like adding water and a salt. Therefore, the finished magnetized needle, or the magnet, is like the carboxylate anion, or soap. The magnet is like the soap because both of them have two properties. The magnet can point north or south, and the soap is both nonpolar and polar. This is why nonpolar parts of the soap can attach to dirt particles or oil, and the polar parts can attach to water, moving the soap and the dirt away from the material you're washing. The magnetized needle, in a similar way, can latch on to the magnetic fields of the Earth and point north. Next, let's take a look at some of the common applications for base-promoted ester hydrolysis. In the human body, saponification reactions are the starting point for all lipid metabolism. Over here is the starting point, and the lipases are the specific enzymes that facilitate this reaction by breaking down fat and gaining energy. The fatty acids and monoglycerides are broken down into salts, which form micelles. These micelles then leave the intestinal lumen, entering epithelial cells and linking to form triglycerides. The most major application for saponification is the creation of soaps, specifically hard soaps. When sodium hydroxide is used as the base in the ester hydrolysis, the sodium cation links up with the polyatomic anion to form an ionic salt and a glycerol. The triglyceride is almost always animal or vegetable fat. If the carboxylate anion in the salt formed is a fatty acid, then the product over here, or the soap molecules, are able to form both nonpolar and polar sides. This unique property is due to the R group, a long nonpolar carbon tail attached to a polar sodium cation at the end. Therefore, the nonpolar end will dissolve grease and oil, while the polar side will allow the soap to be washed off with water, forming polar bonds with the partially negative sides of the oxygens in water. Soap is therefore very effective because lots of oil and dirt are composed of nonpolar oils. When soap interacts with an oil molecule, it forms a micelle, shown here. When the water is washed away, the oil molecules are emulsified into tiny little droplets and leave along with the water. A third application for saponification is the making of soft soap, as compared to hard soap seen here. For making soft soaps that are liquid, you have to use potassium hydroxide rather than sodium hydroxide. When making soft soap, there's both a one-step and two-step process. The one-step process is more frequently used, but in the two-step reaction, hydrolysis produces carboxylic acid rather than the carboxylate anion. Therefore, the second step process is slower, but it allows for fatty acid purification, therefore increasing the quality of the soap. Soft soap, for example, would most likely be using a one-step reaction, while higher brands of soft soap would be using the two-step reaction, being more expensive but also higher quality. A fourth application for saponification is the creation of wet fire extinguishers. The base-promoted ester hydrolysis converts burning cooking oils and fats into non-combustible soap. Additionally, because the reaction is endothermic, meaning it absorbs energy or heat, it also helps to extinguish the fire because it lowers the temperature of the environment. Wet fire extinguisher ingredients are the products of a base-promoted ester hydrolysis using potassium hydroxide and an ester. Normal fire extinguishers are useless for dealing with cooking oils and fats because they have a flash point above 37 degrees Celsius. So wet chemical fire extinguishers are mandatory in restaurants and kitchens.